Hello everyone, my name is Berke Yaman Sungur and I'm an electrical and electronics engineering student at Bilkent University. And in this video, I am going to present to you the experiment that I designed for my class Physics 101. In this experiment, our primary goal is to calculate the spring constant of a spring through the conservation of energy. The experiment consists of two parts, part A and part B. In part A, our goal is to calculate the gravitational acceleration. We will use an airtable tilted to a previously known angle, theta, and a puck that will be released from the top of the airtable without initial velocity. We will measure the distances between the marks on the paper, which was on the airtable, left by the spark timer, and using the recorded measurements, we will calculate the acceleration of the puck on the airtable. With the acceleration known, now we can calculate the gravitational acceleration through the following formula on the screen, which can be seen as derived from the Newton's second law. In part A of our experiment, we're going to calculate the gravitational acceleration. We're going to use our tilted airtable and drop the puck from the top of it while the spark timer is running. As expected, the puck left marks on the paper with time intervals of 50 milliseconds. By assigning the first mark as x0, the distance between the first 10 marks were measured. Then the data was recorded in a table, then the distances were graphed according to time. Now we have the necessary data to calculate the gravitational acceleration using the mentioned formulas. First, we get the acceleration of the puck by using the kinematical equation x equals 1/2 at squared. And with the acceleration known, we get g by dividing the acceleration by the sine of the angle of inclination. Now we move on to the part B of the experiment. In this part of the experiment, our main goal is now to calculate the spring constant of the spring we are using. I carefully constructed the setup of tilting the airtable to a known angle with a wooden block and placing a spring with an unknown spring constant at the bottom of the airtable and conducted the experiment by releasing the puck from the top of the tilted airtable on course for collision with the spring as described. Now in part B, our aim is to calculate the spring constant. Once again, we're going to use our tilted airtable and we're going to drop the puck and let it collide with the spring. As expected, the puck left marks on the paper with time intervals of 20 milliseconds. The time interval for the sparks was intentionally chosen as smaller than part A in order to better observe the spring's compression. The distance between the puck's releasing point and the spring's equilibrium position and the length of the compression of the spring was measured. The mass of the puck was already known as 420 grams. Then the data was recorded in order to make the necessary calculations to find the spring constant. Now we know enough to calculate the spring constant through the formula on the screen, derived from the conservation of mechanical energy. We use g as the gravitational acceleration we found in part A of the experiment. Then we get the spring constant by plugging in all the values in the formula. I found out that during the experiment, although the results I got were fairly close to the actual values, the accuracy of these values depended on a couple of things like the accuracy of the measurements in part A and the spring bouncing after the collision in part B. However, it would not be a realistic prediction to get the exact values in both cases, as there were ineliminable error sources like the friction of the airtable.